Hello everyone, I'm Takamitsu Tajima of Honda R&D. My presentation today will concern conductive electric load system for heavy-duty trucks. My presentation will follow the order shown here. I will begin by discussing the background and the aim of our research in order to provide an overview. Looking first at the background to our research, the achievement of zero emission during vehicle operation will be an important factor in our effort towards the realization of zero CO2 societies. Vehicles that operate using motor power alone and do not use generators employing fossil fuels as a source of energy will be essential to the achievement of this goal. We therefore believe that evolution of the EV and FCV will be a key focus. However, the EV presents a number of serious issues, the main being cruising range, charging, and a decline in dynamic performance due to increased vehicle weight. We believe that there are broadly two ways to address these EV-related issues. One is to boost battery performance or to increase the number of batteries fitted in the vehicles. The other is to supply power to charge the vehicles while they are in operation, that is, to realize ERS. Now, I'd like to describe ERS. This means that battery installation can be reduced to 1/10 the amount. In other words, the production of lithium-ion batteries can be continued 10 times longer. This was the background to our development of the high-power ERS that I will be discussing today. The aim of our research was to realize an unlimited driving range for EVs by charging the vehicle using large amounts of power while they are in operation. The realization of unlimited driving range in this way would offer users freedom to operate the vehicle and to stop and get out just as they please, without constraint imposed by the necessity of charging. Today, I will be discussing a ERS at 150 km per hour using a power of 400 kilowatts, a DC voltage of 750 volts, and a current of 600 ampere. We consider the power supply from in load at the first stage. In the wireless type, there are safety issues related to electromagnetic noise. In both types, there are issues with falling matter, positioning, and load maintenance. This table compares different methods of ERS. Wireless type and conductive type charging methods are compared. Based on these considerations, we decided that a conductive type system that supplies power from the side would represent the most effective system. This slide shows the contact type system. The previous contact type was sliding plate type using in railways, LRTs, and buses. Our system is a new principle that considered from the automotive society and is a rotating roller type. This method is applied from passenger cars to heavy-duty trucks. Here, we see an overview of the ERS. The system comprises a ERS and a dynamic charging EV. The main infrastructure consists of a high-capacity storage battery and ERS lanes. The vehicle is provided with a power collection unit, a dynamic charger, an instantaneous charging battery pack, and a standard EV system. Next, I will consider the associated infrastructure. The ERS lane can be created by mounting trolley wires on an existing guardrail. The screen shows a magnified view of positive and negative trolley wires attached to guardrail in a V-shaped configuration. Protective covers made up of insulators and insulating materials are fitted around the trolley wires. simply by pushing from the side against the trolley wire in their V-shaped configuration arrangement. The power collection unit hides in centered and the rollers make the desired contact. We have applied Japanese rail safety standards. Let's look at the system overview in greater detail. The pink section here represents technologies that had not previously existed. DC power is supplied to the ERS LAN from the high-capacity storage battery. The ERS LAN supplies DC power to the vehicle. On the vehicle side, the power is collected by the power collection unit and provided to the operating motor and the battery simultaneously by the dynamic charger. Each of these systems is controlled by an integrated control ECU. Next, I would like to talk about the simulation result. This slide shows an overview of simulations that were done. One section of expressway in Japan was chosen as a simulation course. The area distance is approximately 100 kilometers and the difference in elevation is 380 meters. This figure shows the ERS simulation result. The simulation conducted here covers the case of passenger cars and heavy-duty trucks driving in an expressway and carrying a dynamic charging. The ERS power was set at 450 kilowatts. These are the conditions that apply in case of passenger vehicle as EV traveling at 100 km per hour on an expressway. It is charged over 2.7 kilometers in a section 50 kilometers long. In the case of a heavy-duty truck that travels at 80 kilometers per hour, it is charged over 15 kilometers. The vehicle has to have battery with at least approximately 100 kilowatt-hour installed. This figure of 100 hour is the same battery capacity as a large passenger EV, Tesla Model S. Let's look now at the result of test of the system. To continue, I will look at our prototype vehicles. We created 5 prototype models. Passenger car, racing car, and logistic vehicle. Next, I will consider the associated test course. We are carrying out the learning test, the JARI, Japan Automobile Research Institute oval course. Today, however, our heavy-duty truck will be the main focus. Our heavy-duty truck is able to charge using a power of 450 kilowatts at a voltage of 750 volt and a current of 600 ampere at a vehicle speed of 80 kilometers per hour. This video shows the vehicle charging at a power of 450 kilowatts. Heavy-duty truck enters the ERS lane. The driver pushes the button. After power collection arm is open. This is existing guardrail type. After finish charging, driver closed the power collection arm. Here we see the test results. The horizontal axis shows charging distance and the vertical axis shows voltage, current, and power. The results show the vehicle being charged at a speed 80 km per hour using a power of 450 kilowatts. I will now consider the future outlook for this technology. The goal of our research is promotion of substitution of internal combustion engine vehicle and realization of carbon-free society by ERS. I'd like to establish the basic technology and aim for real social justice to develop and put into practical use the technology of the race and the general society. Here we see an image of the future of this technology. In the future, high-capacity storage battery will be charged using recycled energy and will supply this energy to the ERS charging lanes. In addition, multiple vehicles will be able to dynamically charge in the same lane. This is a stationary charging system. Rollers placed on the infrastructure side rotate to radiate heat. That brings me to my conclusion. Allow me to sum up my presentation. The one merit is the reduction in installed batteries, 1/10 the amount. Second merit is ultra rapid charging, 450 kilowatts power. Infrastructure and the vehicle system able to realize ultra high power and high vehicle speed ERS were developed. Simulations of ERS illustrated the conditions for realized ultimate driving distance for EVs using ERS. In the future, we intended to continue to efforts further increase vehicle lineup and boost the reliability and safety the ERS, attempting to realize practical application of system at an early stage in increasing its power. Thank you for your attention.